Herve Gaussier today in our seminars, and he will speak on invariant metrics on domains in CN. Please, Herve.
So thank you very much. It's really a nice pleasure to give a talk, even if it's not a physical talk in Roma, but I'm really happy to be here with you. So I will talk about invariant metrics on domains in CN, as you mentioned, and maybe some of you already heard at least a large part of the talk, but I thought it was interesting to see the connections we had between different sorts of curvature in domains. Of course, when we talk in domains, we can start with a C, meaning in one complex dimension, but I will go directly or quite fast to a higher dimension. The motivation goes, can you see the next page here? Yes?
Yes, we can. Very good.
The plan of the talk is the following. I will start with one complex dimension, but briefly, I will recall what the Poincare metric is, and with in mind some generalizations of metrics and the notion of curvature that is behind. So then invariant metrics on complex manifolds will arrive quite naturally, and then I will talk about curvature properties. Of course, when we mean curvature properties, it can go in different directions. One of them comes from complex geometry or CR geometry. The other one comes from Kähler geometry, and it can also come from metric properties or metric geometry. And I will try to give you some link between all these kinds of properties and so of geometries also. So let's start with the Schwarzpick Lemma. As you know, if you consider a holomorphic map from the unit disk, D here means the unit disk in C. So if you consider a holomorphic map from D to D, then you have an inequality satisfied by the map F and its derivative. The quotient mod of the F prime of Z over 1 minus mod of FZ squared is less than 1 over 1 minus mod of Z squared. So this is an inequality, and you can view this really as an analytic inequality. And the proof is very natural, and it's quite easy. It's easy because we know the structure of the automorphism group of the disk. It's a homogeneous domain. And so you can start with the origin. You say the origin to the point Z, the one you consider because you want to evaluate F at Z. And it's via some automorphism phi of Z. Then you apply your map F that sends Z to F of Z. And then you send by another automorphism F of Z to the origin. And so by the composition of these maps, you have a map from the unit disk to the unit disk that sends 0 to 0. And then you know, of course, that it satisfies the usual Schwarz lemma. And it's really then using the usual Schwarz lemma, meaning that the derivative of the composition has modulus less than 1, less than or equal, that you arrive to this inequality. But of course, this inequality, everybody knows now that there is something behind that comes also from geometry. And it's given by the Poincare metric. So the Poincare metric is a metric, you can consider it as a Riemann metric, and it's defined as you can see on the slide. So if you evaluate at a vector V, it's at point Z, Z is in the disk, and you evaluate it at a vector V in C. And the norm squared is given by mod of V squared over 1 minus mod of Z squared squared. So it's exactly the meaning of the infinitesimal version of the Poincare metric. And I just wrote two other things. The first is that it has some curvature, and the curvature is constant on the disk. When we talk about curvature here, we mean the Gauss curvature. If you have a metric, of course, there's a way to compute it. And you can compute by saying that if you consider the Poincare metric, it's given by a squared dz wedge dz bar. And then you have a formula that tells you precisely how to compute the Gauss formula, the Gauss curvature, And then you arrive to the fact that the curvature of the Poincare metric is constant, and it's negative. Some people write -4, some people write -1. It really depends where you come from. If you come from differential geometry, it's one of them. If you come from complex analysis, it's the other one. Here, I just wrote that it's -4, and it's just a normalization problem. But what is also important is if you have in mind the definition of the Poincare metric, then the inequality we had just tells you that a holomorphic map decreases the metric. It means the metric decreases under the action of holomorphic maps. In particular, if you have an automorphism of the disk, you will just have an isometry. That's what we say, that the Poincare metric is an invariant metric under the action of holomorphic maps. And so here, this formula, of course, it's easy to prove now when you have the definition of the metric, and we proved the Schwarzpick lemma. But it's quite mysterious because we don't see the metric appearing. But in fact, you have the Schwarzpick Alfors-Yau lemma that tells you the following. Imagine you consider some Riemann surfaces, two Riemann surfaces, S1 and S2. You assume that S1 has some Riemann metric G1 that is complete. And S2 G2 is not necessarily complete. And you make two assumptions. The first one is that the curvature on the first Riemann surface S1 is bounded from below. And the second one is that the curvature on the second surface is bounded from above by a negative constant. The fact that the first one is bounded from below by a negative constant is always satisfying as soon as it is bounded from below, because you can always put a negative constant. What is important is the fact that on the second surface, you assume that the curvature is bounded from above by a negative constant. You have to keep in mind the hyperbolic surfaces for which it's constant and it's negative. So it's really in that kind of vein. And now, sorry, you consider a holomorphic map between these two surfaces. Then you have an identity, sorry. It tells you that the map decreases. So decreases, it tells you that you have exactly the same kind of inequality you had in the case of the disk, except that now you see precisely the curvature appearing. And what you get on the right side is the quotient of the curvature. So you see in the case of the Schwarzpick lemma, of course, A1 equals A2 equals -4. So that's why you get really the decreasing under the action of holomorphic maps. So now you see it's much more interesting because the curvature of the manifold or the curvature of the surface here appears really in the inequality you obtain. There is a generalization of this Schwarzpick Alfors-Yau lemma, and it's called the Yau-Schwarz lemma, and it works for any complex manifold as soon as you get some condition on the curvature of your manifold. We'll see it later, and we will use it in the presentation. But now if we go back to the Poincare metric, as I mentioned, you can consider a point in the disk, a vector in C, and you compute the norm of the vector for your metric. And it's just mod of V over Y minus mod of Z squared. Of course, I did not mention it, but it means that imagine you take a vector in C that has constant Euclidean norm equal to 1, for instance. You see that the norm of the vector moves with the point when the point goes to the boundary, and the norm of the vector for the Poincare metric goes to infinity when you go to the boundary of the disk. There are two different ways. Of course, there are many others, but I think there are two very interesting ways to see this quantity, mod of v over 1 minus mod of z squared. And it really relies on the characterization, on the description of automorphisms of the unit disk. The first way is to consider, you can view mod of v over 1 minus mod of z squared as the infimum of this set. So it means you consider a map that sends the unit disk to the unit disk, and it sends the origin to your point z, because you want to evaluate at point z. And you just compute f prime of 0. Of course, here we are in dimension 1. The fact that f prime of 0 is collinear with v is natural because we have only one dimension. But keep in mind that in higher dimension, it will be completely different. So it will be already an extra condition. And you just normalize by some alpha, and you compute the infimum of such alpha for which there exists such a map. If you do that in the case of the disk, it's reached, and it's reached exactly by the automorphism that sends, by an automorphism that sends the origin to point z. But now there's also another way. You can evaluate mod of f prime of z dot v for all f from d to d, not sending 0 to z, but your point z to the origin. So it's a dual way. Either you send 0 to z, or you send z to 0. And if you take the supremum, in case of the disk, it's still reached, and it's reached really by an automorphism sending z to 0. So you consider the infimum, you consider the supremum, and you get two quantities. What is really remarkable here is that now not everything is fixed in these two definitions, because what is fixed is if we consider 0, it means we are really in the unit disk. But if we consider a point z, we can be in any complex manifold. In particular, if you look at the first equality with the infimum, you could replace the target domain D by any complex manifold, sending f of 0 to a point z that is a prescribed point in your complex manifold. And you can consider this quantity. On the second one, still, since we deal with a map that sends z to 0, it means that the starting domain D here could be replaced, the original domain, by any complex manifold M. You could consider a map F from a complex manifold M to the unit disk, sending a point Z to the origin. And you can consider these two quantities here, and you get exactly what we call the Kobayashi and the Kara-Theodori metrics. I should have mentioned that when I deal with, when I mean metric, when I call what I call metric here, is really an infinitesimal metric, meaning that we compute the norm of a vector in a complex manifold evaluated at point Z. So we consider M a complex manifold, Z a point in the manifold, and V is a tangent vector. And we define these two quantities, K is for Kobayashi and C for Kara-Theodori. These are two infinitesimal versions. Of course, I'm sorry, in the definition of the Kara-Theodori metric, there should be a mod here, right? Because it has to be non-negative. And this defines you two pseudometrics, because what you know is that they are well defined, but what is not clear is if they are 0 or not. They may be identically 0. Then you have a way to compute the length of a vector. But it means that you can compute a distance between points just by integrating these pseudometrics. I just wrote it, the integrated distance for the Kobayashi metric, and it's just given as the infimum of the over all the curves joining. So you consider 2 points Z and Z prime in a complex manifold M, and you consider all the curves, C1 curves, let's say, or piecewise C1 curves joining Z to Z prime, and you consider the Kobayashi pseudometric at point gamma of t and you evaluate the size of gamma prime of t, you integrate it, and you take the infimum over all the curves. And it gives you the Kobayashi distance. You can do the same with the Carthe-Theodori metric, and you get a Carthe-Theodori distance. So now, just one or two definitions. We say that M is Kobayashi hyperbolic if the distance we defined just above is really a distance, and it will give the topology you want on your manifold. And you say that M is complete hyperbolic if the metric space M is your complex manifold with the distance Km is complete. Of course, you just need first that it's really a metric, a distance for it to be complete. I just added also that it were geodesic. It's just because if it's complete, due to the fact that it's given it's a length space, it will be geodesic, meaning given 2 points you can join. Some examples. The first example is the unit ball. So the unit ball, on the unit ball, the Kobayashi and the Carthe-Theodori metrics are equal. And there are really just generalizations, but direct generalizations of the Poincare metric in the disk. It's quite easy to compute the Poincare, the Kobayashi, Poincare, or Carthe-Theodori metric here, just because the unit ball is homogeneous, meaning that the automorphism group is transitive. So you can compute everything at the origin. It's just given by the Euclidean norm. And then you know precisely the structure of the automorphism group, so you can compute at any point using the fact that the automorphisms are isometries for your matrix. I just gave two versions of the unit ball. Bn is really the unit ball, the norm of z less than 1, and Hn is the unbounded version. But you also have Dn. Dn is the polydisk, so it's a copy of Dn times, and it's also complete hyperbolic. Now, if you have a complex manifold M that contains an entire line, meaning the image of C by a non-constant holomorphic map, then it won't be hyperbolic. And it's easy to see because if you look at the definition of the Kobayashi pseudometric here, when you look at the infimum, if you can put larger or larger disk, it's as if you could put maps with alpha that are bigger and bigger, larger, smaller and smaller. Sorry, because imagine you put larger and larger disk with norm 1, because imagine exactly what happens in C. If you reduce to the unit disk, it will just tell you that you have larger and larger derivatives. So alpha, you can choose it as large as small as you want, because V over alpha will go to infinity. So it means the Kobayashi infinitesimal metric will be identically 0. But now if it's the case on C, since it decreases under the action of holomorphic maps just by definition, it will be identically 0 of f of C, and you can see by also the fact that f of C is contained in M, that M won't be hyperbolic, meaning that the Kobayashi metric won't be a metric on M, because on f of C, it will be degenerate. Finally, another example, if you consider a convex domain in Cn, then you have an equivalence between the fact that it's complete hyperbolic and the fact that it does not contain non-trivial entire lines in the domain. Oops, sorry. It doesn't work if I'm doing it this way. So the Kobayashi and the Carthe-Theodori metrics are the first type of metrics I considered. And as you see, we just consider the norm, we compute the norm of a vector. And there is no structure, it's just a Finsler metric. But now we will study another type of metrics that is a Keller metric. So here we go to higher dimension and we consider a bounded domain in Cn. I will consider it also pseudo-convex. Pseudo-convex is the complex invariant of convexity in the real case. So convex is not invariant under bihomorphisms, but it's replaced by the notion of pseudo-convexity that is the natural one because it's invariant under bihomorphisms. I will consider two types of metrics, two different metrics. The first one is the Bragman metric. If we consider a bounded domain, we know that the space of functions that are holomorphic and with a square bounded, the norm squared bounded, gives you a Hilbert space. And so you have a representation formula by the Riesz formula. So you have a kernel and it's defined, it's called the Bragman kernel. And if you consider the second derivative of the log of k over dzi dj bar, then it gives you a metric. And this metric is considered as the Bragman metric. There's another sort of metric, the Keller-Einstein metric. And it's a solution of a Monge-Ampère type equation. On the domain, it satisfies the identity given here. And you also want that it explodes near the boundary. Here, the explosion is at the infinitesimal version, but it will give you also, when you integrate, it will give you explosion, meaning a complete metric, so explosion of the distance. So here we have two metrics. Why did I consider a pseudo-convex domain? It's because in the case of the Keller-Einstein metric, the existence of such a metric is far from being trivial. And it was proved by Cheng and Yao on strictly pseudo-convex domain. Just consider them as being deformation of the unit ball. And later, it was also the existence and the uniqueness with prescribed Ricci curvature was proved by Mock and Yao. So that's why I consider, if you want to consider Keller-Einstein metric, you deal with pseudo-convex domains and bounded pseudo-convex domains in Cn. Now, of course, I defined two kinds of metrics, Finsler metrics on one side and Keller metrics on the other side. But you can ask, these metrics, are they the same? Are they different? If you consider on the ball, of course, if you consider on the disk, there is only one metric with a prescribed curvature, and it's the Poincare metric. So all these metrics are natural generalizations of the Poincare metric. If you consider the unit ball in Cn, they are equal. Of course, it depends on the Ricci curvature you consider, but you can find one such that they are equal for the Keller-Einstein metric. But what happens on a general manifold or on a domain, even on a pseudo-convex domain bounded in Cn, there is a conjecture due to Cheng that tells you that if you consider a pseudo-convex domain, and if you assume B is for Bragman here, if you assume that the Bragman metric is Einstein, meaning that by choosing the right normalization, it's the Keller-Einstein metric in your domain, then your domain has to be homogeneous. So only it will be quite a very special domain. If you consider, for instance, the polydisk, it's not, no, on the polydisk is a special case, sorry. But so this conjecture was proved for a certain type of domains that are strictly pseudo-convex domains. So it was proved in a special case by Nemirovsky and Shafikov, and then in the general situation by Wang and Chi. And they proved that if you consider a strictly pseudo-convex domain in Cn, let's say, and if you assume that the Bragman metric is Einstein, then necessarily the domain is the unit ball. Of course, if you make an assumption about simply connectedness and so on. So you see, it's very particular to have a domain for which the metrics coincide. I should mention also that I didn't say anything about the link between Finsler metrics we considered on one side and Keller metrics. And we proved, or we study the case where about for the Kobayashi metric, and we can prove, we worked on that with Andrew Zimmer, and we can prove that if you consider strictly to the convex domain in Cn, and if you assume that the Kobayashi metric is Keller, then under some condition it will be the unit ball. So you see, all these metrics are really defined differently, and in the general situation, they are very far from being equal. So what we will be interested in is understand some kinds of geometry. If you deal with Keller metrics, you have a metric that is defined and that has some regularity, and you can study different objects associated with your metrics. You can, for instance, as I told you, the metrics are complete on your domain or sometimes on your manifold, but you can try to understand the behavior of geodesics, even geodesic rays. So you fix a point and you try to understand how they escape and how they go to infinity. Because even if you consider a bounded domain, if your metric is complete, you see the boundary as the boundary at infinity. So you can try to understand estimates of the metric, but also estimates of the curvature. And as I just mentioned, the shape of geodesics. What do we mean by estimates of curvatures here? We deal with complex manifolds. So the curvatures, we will consider horomorphic curvatures. There are essentially one type, but let's say two. The first one is the bisectional curvature. Or here is the Riemann tensor. So you evaluate, you consider two vectors x and y, and you consider the Riemann tensor, and you evaluate it at, of course, when I say x, jx, y, gy, it just means that I prescribe the point and I consider tangent vectors at that point. And so you consider the Riemann tensor, and you divide by the norm squared of the vectors. The special case is where you assume that you get only that x and y are the same, and you get the horomorphic sectional curvature. The first one is called the bisectional curvature, horomorphic bisectional curvature, and the second one is called the horomorphic sectional curvature. It's just the horomorphic sectional curvature is just the sectional curvature restricted to a complex line. You can define the sectional curvature for any two vectors that are independent. And in the special case where the two vectors, for instance, y equals jx, then you get the horomorphic sectional curvature. So what we want to understand is how these curvatures behave in the case of some complex manifolds, and essentially in our case, in the case of domains. So I told you before that there was a generalization of the different Schwarzpick lemma I mentioned at the beginning in the context of Keller manifold. So now you consider a complete Keller manifold M endowed with some Keller metric G, and you assume that the Ricci curvature is bounded from below. And you consider N is a Hermitian manifold, and you assume that the bisectional curvature is bounded from above by minus C2. In the case of a domain in C or a Riemann surface, Ricci, bisectional, horomorphic, all the curvature will be the same. You get only one. So you get these two conditions that are exactly the conditions you get in dimension one. and you consider a holomorphic map from M to N. Then you have a decreasing for holomorphic maps, and it's given in terms of the curvature, exactly as we had in one complex dimension. So keep it in mind because we will use it. Just maybe a remark here. Imagine you assume MG is just the unit disk with the Poincare metric. It will tell you that you consider a holomorphic map from the unit disk to some Hermitian, but let's say even imagine it's a complex manifold M, or even a Kähler one. But if you started with M being the unit disk, of course the curvature is constant for the Poincare metric. So you can apply such an inequality. But now imagine you assume that N with H is the unit disk with the Poincare metric. You will consider a holomorphic map from your complex manifold or Kähler complex, complete Kähler manifold here to the unit disk, and you will get an inequality. In the first case, when M is the unit disk, it will tell you that you can compare your prescribed Hermitian metric H with the Kobayashi metric, because you will compare with the Poincare metric from above on the disk. In the second case, where N is the unit disk, you will compare your metric from under with the Carl-Theodori metric. So please really keep that in mind. In case M equals the disk or N equals the disk, you will compare a metric on your manifold. Of course, your manifold will need to have some curvature conditions to satisfy some curvature conditions. And you will compare either with the Kobayashi metric or with the Carl-Theodori metric. What is known about the behavior of the horomorphic bisectional curvature on domains? In fact, there are very few things that are known. As I told you, probably the most important result in the field is due to Cheng and Yao. And they proved that every strictly pseudo-convex domain admits, let's say bounded, admits a Kähler-Einstein metric. This one is complete on D. If you prescribe the Ricci curvature, it will be unique. And the holomorphic bisectional curvature is negatively pinched near the boundary. It's really important to also have in mind the fact that all we consider is really near the boundary. You can deform, you don't know what happens inside the domain in general, because the geometry of the domain is just defined here by the geometry of the boundary. So all the estimates or all the asymptotics you may wish to have are valid only near the boundary. There is a result by John Bland in the same direction. And in the same direction, you consider it's an egg. It's not an ellipsoid because it's not a real ellipsoid, but it's an egg. And in that case, in C2, John Bland proved that the Kähler-Einstein metric is also negatively pinched. Sebastian Gontard considered the case where you have an unbounded domain, because you replace, of course, you could replace repart of z by mod of z squared, but you replace mod of z2 to the power 2m by repart of w squared. So it's unbounded, and the Kähler-Einstein metric still has negatively pinched holomorphic bisectional curvature. In contrast, if you consider the polydisk, it does not admit such metric. So if I try to be more precise, it tells you the result by Paul Young, tells you that the polydisk, on the polydisk, there is no complete Kähler metric with negatively pinched holomorphic bisectional curvature. As an example, consider the Bragman metric. It has bounded negatively pinched holomorphic sectional curvature. But if you deal with a sectional curvature, you deal with disks. So you can do everything at the origin because the automorphism group is transitive. And at the origin, it's just as if you were in the disk. But of course, you get a different disk when you go to the diagonal direction. But if you consider now the vector 1, 0, imagine you are in D2, so in complex dimension 2. You take a product, two products of the unit disk. Then the holomorphic bisectional curvature of the Bragman metric is 0 if you evaluate at vector 1, 0 and 0, 1. And it was generalized by Harish-Seshadri to the case of a product of complex manifold. If you consider a product of two complex manifold, it does not admit a complete Kähler metric that has negatively pinched holomorphic bisectional curvature. So I just tried to draw, no, I took the pictures on internet, of course. So it tells you in the first case, the ball is not equivalent, is not bihomorphic to the bidisk, and the ball is not bihomorphic to the egg. As I told you, the first way to prove it, of course, there was a former proof due to Poincare, at least for the ball and the polydisk. But keeping in mind what we just said before, what can be an abstraction? The first abstraction comes from Kähler metric. If you look at the Kähler metrics on the ball, they are all equal, and you can prove that it's negatively pinched. It's just because when you look at the holomorphic sectional curvature, it will be constant here. But on the bidisk, it's not. And here also, it's just because for the same reason, because you can have estimates on the curvature. So you see, this is a little complicated proof of the fact that these objects are not bihomorphic. A second kind of abstraction comes from Cauchy-Riemann geometry, meaning the boundary of geometry. As soon as we are in complex dimension, at least 2, it means that the boundary, if you consider a domain, the boundary has at least real dimension 3. It means it can contain complex objects. It does not necessarily, but it can. And so what we are interested is, for instance, the existence of objects, holomorphic objects that are tangent. So why is the ball and the ellipsoid not equivalent? It's just because if you consider the order of contact between the ball, meaning the sphere here, the boundary of the ball, and the holomorphic disk, the highest order of contact is 2. In the case of the polydisk, here you can say, in this case here, you can prove that it's 2m. It's easier to see if you don't know anything even about complex geometry in the case of the ball and in the case of the polydisk, because in the case of the ball, it will be it will be 2 also. I should not have mentioned here the boundary of delta n, it were en. But if you consider the polydisk here, it would be infinity, because you can have disks that are contained inside the boundary. And so we arrive to the definition of the D'Angelo type, that is the maximum order of contact between the boundary of your domain and the holomorphic disks. To make things easier, we deal with smooth almost everywhere, as in the case of the bidisk boundaries. So you see here there is another type of geometry, and from the Euclidean case, from the Euclidean point of view, we understand more this geometry because it's quite visual, the geometry of the boundary. And so what we're interested in is to understand the link between the type, so the order of tangency of disks, meaning CR geometry of the boundary, and Kähler geometry of the domain, meaning, for instance, the behavior of the curvature of the domain. And a quite natural question in that direction is, imagine you consider a bounded pseudo-convex domain in Cn. When is the following condition true? the domain, you assume it's the boundary is smooth, and the boundary is of finite type if and only if the bisectional curvature of some Keller metric is negatively pinched. So you see, it's a quite vague question because we did not prescribe any metric, and it could be here, G could be the Keller metric, Keller-Einstein metric, it could be the Bragman metric, but we can also imagine that it's some metric. And what is important to understand here is that we need some extra assumption because of a theorem due to Fornes and Wrong. They prove that there is a domain, it's also explicit, there is a domain in C3 that is pseudo-convex or finite type with a smooth boundary. But when you look at the Kobayashi metric, it's by Lipschitz, it's not by Lipschitz to any Riemannian metric. So you can wonder, yes, but what is the link? And the link is due to a theorem by Wu and Yao, a recent theorem. And they prove that if you have a domain, if your domain here had a complete Keller metric such that the horomorphic even sectional curvature were negatively pinched, then the Kobayashi metric would be bi-horomorphic, for instance, to the Bragman metric. But here it's not the case because it's not by Lipschitz, would be by Lipschitz, sorry, to the Bragman metric. But here, in their example, in their theorem, it's by Lipschitz to any. It's not by Lipschitz to any Riemannian metric. So you see, you are forced to add some conditions to hope to get an equivalence in the previous section question. So I will just mention here until the end, I will work on that theorem, a theorem we proved with Filippo Bracci and Andrew Zimmer. As I told you, you need some extra condition, extra assumption on your domain. Here we consider a domain in Cn, not necessarily bounded, and we assume it's convex. So this is a strong assumption, but it's the assumption, we need some assumption. And we assume that the domain admits a complete Keller metric that is negatively pinched outside some compact set. If the domain were bounded, we would just have said near the boundary. But here the domain is not necessarily bounded. So it's outside some compact set. We don't mind about what happens on a compact set. Then the first point is that D does not contain entire lines. The second, in particular, as I gave you an example when we consider the Kobayashi metric, it just tells you that when you consider the domain endowed with the Kobayashi metric, it's a complete metric space. The second point is that the boundary does not contain non-trivial analytic disks. So it's far from being the bidisk, and that we understand by Young's result. It really goes in the same direction. With that assumption, you are far from having a bidisk or something that is close to a bidisk. And the third condition is if you assume that the boundary is smooth, and we can always assume that the domain is bounded, it's not a big deal here, then the domain, the boundary of the domain is of finite type in the sense of the angle. If we go back to the question before, it just tells that we have one direction. If the bisectional curvature is negatively pinched, then the domain is of finite type. But in fact, it happens that this is also an equivalence, in fact. So I should be careful when I say that. It's just that we have the complete, this direction from the existence of complete Keller metric with horomorphic bisectional negatively pinched to domain of finite type. But it seems the converse is also true, and we work on that still. And there is another theorem that is quite interesting, but I won't give the proof of it, or even a hint of the proof, that if you still assume that the domain is convex, you assume some regularity, the domain is bounded, and regularity is C2 alpha, so a little more than C2. And you assume that the horomorphic sectional curvature is pinched by very close to being constant near the boundary. This is equivalent to being strictly pseudo-convex. You may find surprising the fact that we need C2 alpha, but it's wrong in the case of C2. And C2 alpha, the situation, even the geometric situation, is different in that case. But I won't say more on that. So I will try just to give a sketch of the proof, because it's almost the end. I will try to give a sketch of the proof of the first theorem here. So we will deal with the convex domain in Cn, and we assume that it admits a complete Kähler metric having a horomorphic bisectional curvature negatively pinched outside some compact set. There are essentially 4 steps in the proof of the fact that it's a pseudo-convex of finite type. So it will be, the proof will be by a contradiction. So assume that the boundary contains part of an entire line. Since your domain is convex, it means that it contains part of C, or that it has a point of infinite type. It will be the same. Then you can prove, and this was due to Andrew Zimmer, you can prove that you can find a sequence of affine transformation from your domain to some new domain. And what is important that they are affine, such that the limit domain contains a bidisk. When I mean a bidisk, it's really, when you look, you have an object of complex dimension 2 inside the domain. And if you restrict to this object of dimension 2, the boundary is exactly the boundary of the bidisk here. What is important is your affine transformation converge, and they converge to some domain having this property. What is also important is your domain does not contain an entire line. So it means in particular, as I mentioned before, that it's complete hyperbolic for the Kobayashi metric. So now you have a sequence of domains. All these domains are bihomorphic to your starting domain D, and they converge to some convex domain D infinity. What is important is, due to the fact that the limit domain does not contain entire lines, you have convergence of invariant metrics. What I mean here is, if you consider the Kobayashi metrics of D nu, they will converge to the Kobayashi metric of the limit domain. But if you also look at the distances, they will converge to the Kobayashi distance on the domain. Of course, when we talk about convergence, we mean a convergence on a compact open subset. The third point is the properties of the limit domain. What is important, maybe you can skip the first 2 dots. What is important is the last one, and it's due to Zhang, who proved that your domain, for which if you look at in dimension 2, it behaves like the bidisk, such a domain does not admit any complete Kähler metric with horomorphic bisectional curvature negatively pinched. So if I go back to the previous slide, the situation is quite clear now. You have a domain D, and on your domain D, that is the original domain, you assume you get some metric that for which the horomorphic bisectional curvature is negatively pinched outside the compact set. This is, of course, you can drive your metric to the metric D nu, because you have some bihomorphism to get a Kähler metric on D nu. And you get this Kähler metric, they will be negatively pinched somewhere. And you have domain D infinity. And imagine that the Kähler metrics you had on the nu converge to some Kähler metric on the infinity. Then, by the fact that the horomorphic bisectional curvature at each step were negatively pinched, it will give you that at the arrival at the limit domain the infinity, you would obtain a Kähler complete metric for which the horomorphic bisectional curvature is negatively pinched. And you would use Zeng's result to get the contradiction. And it's exactly the way it works. The difficulty here is that when you look at the assumption on your domain, we just assume that it admits a complete Kähler metric that is negatively pinched, for which the horomorphic bisectional curvature is negatively pinched outside a compact set. But so imagine you consider the images by your linear transformations or affine transformations, you get new metrics, but you don't know anything about the convergence of your metrics. Because in general, these are smooth objects, but to get convergence, you need something very strong in terms of derivatives of your metrics to ensure the convergence. For that, you need estimates of the covariant derivatives of your metric, but we don't have such an assumption. And then we just get this outside some compact set, but we don't know what happens inside. So how to be sure that when you consider your metric at the limit, even if the metrics were converging, that the horomorphic bisectional curvature was globally negatively pinched? These are the issues we meet here, and this is really what we need to work on to get the result. And of course, as soon as we will have constructed, we will have proved that we can deform the metric and that the metrics, the sequence of metrics we consider will converge to a metric, and this metric will have a horomorphic bisectional curvature globally negatively pinched, then we will get the contradiction by Zeng's result. But for that, we really need to work a little more. I will just mention the fourth step, and then I will probably stop. I can continue later if you want, but I will just give you what is missing now. And what is missing is a deformation of metric. So we had a complete Kähler metric on D, and we assume that it's negative. The horomorphic bisectional curvature is negatively pinched. This is just outside the compact set. Fix some positive constant epsilon, and then there is a result due independently to Kapovich or to Xi that tells you the following. You can deform your metric to a new complete metric. This is a manifold case, but it works here in the case of our domain D, to a new complete Kähler metric in such a way that the deformed metric is very close. So that's why you fix some epsilon. The deformed metric is very close to your previous metric on the domain. And when you look at the bisectional, you can do that for any prescribed curvature, in fact. But the bisectional curvature is sufficiently close to the bisectional curvature of the original metric. Of course, this is only purely local. So you have to fix some R also, and it will be only on some small ball centered at a point. But in our situation, of course, it tells you that the curvature is very close to the curvature of the original metric. As soon as you are sufficiently close to the, you don't move too much from one point to the other one. And the third point that is very important is that the covariant derivatives of your new matrix are uniformly bounded. Here, you have everything you want to be able to dilate, so to consider the affine transformation A nu. And you will have, instead of working with G, you work with the new metric G tilde. Since the holomorphic bisectional curvature of G is negatively pinched outside the compact set, you will get the same property by point 2 for the new metric G tilde. They are very close to each other. And now the covariant derivatives are bounded uniformly. So it tells you that you can dilate and you can consider the limit. And the derivative of the limit will be bounded, meaning by point 3 that your sequence of metrics, the dilated metrics, will converge to some metric. But it will be only a pseudometric. But by point 2, in fact, by the assumption, you can compare your metric G with the Kobayashi metric. We know that the Kobayashi metric converge to a metric here on a Kobayashi metric that is non-degenerate on the limit domain. So you will get exactly by point 1 the same assumption for the new metric G tilde. And so for the dilated metrics, they will be comparable to the Kobayashi metrics. And so they will converge to something that is comparable to the Kobayashi metric on the limit domain. So it finally means that on the limit domain, the infinity after dilation, you construct a complete Keller metric that is comparable to the Kobayashi metric. But from point 2, what was just local will become global by dilation. So your limit metric, your Keller complete metric on the infinity, will be negatively pinched. The holomorphic bisectional curvature will be negatively pinched. And then you will get the contradiction by the Zhang's result. I think I will probably stop here for the presentation, but I can continue if you have questions, and I will be very happy to answer your question if I can. Thank you very much.
Well, we thank Herve. Thank you for the very nice talk. And I'll start to see if are there any questions. Well, maybe I can start with some questions. I'm sorry, I have some very naive, basic questions. First of all, in this, your last theorem, are you assuming that the boundary is smooth, or is? I'm sorry, if you go to the statement, you talk about D is convex.
So if you look at the statement,
yes,
I try to focus more or less on the third part, right? Because I want to prove that it's of finite D'Angelo type. I assume by contradiction, I should have been more precise. You're right. You assume by contradiction, I assume that it has a point of infinite type. So I am in the point 3.
Okay.
You probably mean, in fact, we don't need to define the type. We don't need the boundary to be smooth. We can define the type even for non-smooth domains. But here we already refer to the type in the case of the order of contact, meaning when you look at a defining function, you look at the derivative, so it means you need some regularity. And since we don't know what will be the type, we deal with the boundary of class infinity.
Okay.
Do I answer your question?
So it's not a running hypothesis. So you start with literally with the domain D, which is convex, and that's all.
Yes.
Okay.
Yes, because if you look at the first two, I mean, there's a real difference between the first 2 points in the conclusion of the theorem and the third one. The first one does not say anything about the boundary of the domain. So we don't need any assumption on the boundary.
Okay.
The second one is just the fact that you don't get trivial analytic disks. So it doesn't say anything about the regularity either. You can imagine that it's not smooth at some points, right?
Right.
And
Yeah.
but the third one, we want the domain to be globally of finite D'Angelo type. And with the definition we consider, that's why we assume the boundary is globally of class infinity, because we don't know what the type can be. And by contradiction, we assume it's of infinite type, meaning that there are disks or germs of disks that are tangent to higher and higher orders. But for that, we need the boundary to be sufficiently smooth.
Okay.
Any order, and that's why we have this infinity condition.
Okay. Okay. Yeah. Yeah. No, it makes sense. I have another even more basic question. At the beginning, you said that you're looking at these invariant metrics, these metrics, and you studied their behavior at the boundary, because you don't know anything about what's going on inside. But I just always thought that what happens inside the domain, we're talking about the invariant metric on the domain, you're looking at the behavior when you go to the boundary, that inside everything would be equivalent or trivial because they're like C-infinite solution. So everything will be C-infinity, so somewhat comparable. And the actual question is the behavior at the boundary of these metrics. Not that you don't. I mean, it's true that you don't know anything, but everything is, I would think, is somewhat equivalent on a fixed compact set. Say, am I wrong or?
No. You are perfectly right. But it just depends on which level you want to compare. If you compare metrics, you know there are metrics, so they are positive. So by Lipschitz outside the compact set will give you something by Lipschitz globally. You are completely right, and we use it. But I'm talking about holomorphic bisectional curvature.
Okay.
And there's no need. We don't need to assume that it's negatively pinched globally on the domain. And we don't even know if it's true inside. We know what is clear is that it's pinched. But how can you ensure that at one point it will be negative? That we don't know, because we don't know how to compute. As you said, it's a C-infinite solution of something, so it will be irregular. If it's infinity, you can say that all the curvatures will be bounded. But we don't know if the bounds will be negative or not.
Okay.
And of course, negatively pinched really tells something in terms of curvature. But to have a curvature, you need a boundary in some sense, right?
Right.
That's how you can have this assumption close to the boundary, and that's what we have.
Yeah.
But in the same direction, what is quite surprising is you could imagine that the holomorphic sectional curvature were sufficient. I just gave you the example of the bidic that tells you it's not. But the reason is when you deal about the type, for instance, when you consider type is not a one-dimensional object. In fact, it's a two-dimensional object because you look at holomorphic disks, but that are tangent to the boundary. So you compare what happens in the normal direction to what happens in the tangent direction. So intuitively or implicitly, you have a two-dimensional, complex dimensional object. So it's a way to understand why the natural candidate is really the holomorphic bisectional curvature and not the holomorphic sectional curvature here.
I see. Thank you. Yeah. Are there any other questions? Well, then we can thank Herve again. Thank you very much for the very nice talk. And